Okay, so this is what we'll be interested in probability of correct output. So these are the two types of random algorithm we discussed last time. And today what we will do is that there are also, as I told last time, that there are algorithms whose running time and output may both be random. Okay, so then we define the notion of what is the worst case running time for Las Vegas algorithm. Then we also define the notion of what is the worst case error probability for Monte Carlo algorithms. And then, so having defined all those, today we just straight away want to get into randomized quicksort. So what was a randomized quicksort? So this is a randomized quicksort. We pick a pivot element uniformly at random. We pick a pivot element uniformly at random from the array. We split the array. So now you have picked up some pivot. Based on that, all the numbers which are less than this number, you put them in the left array. The numbers which are larger than that, you put them in the right array. So basically by comparing, and then you recursively solve the left part and right part and concatenate them to get the whole solution. Okay, so this is basically randomized quicksort, which all of you have seen several times before. So is this algorithm Monte Carlo or Las Vegas? What could be the error here? Can this algorithm output us a wrong answer? Anybody?
No, it cannot suck it.
Okay, thanks. So it cannot. So this is an algorithm where the thing which we will worry about is expected running time. How much running time does this algorithm take on an average? Okay. So if you recall, what did we say? Hey, the way to analyze a randomized, any quicksort, any algorithm, a randomized algorithm will be that you're given an input X, you look at your source of randomness, R1, R2, dot, 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 RQ, and then based on that, what are you returning? Say YR1, YR2, YRQ, right? And definitely if I get Y, if I go via this route, I have some running time. I go via this route, I have some running time. I go via this route, I have some running time. So what is the running time, expected running time for X? Well, what is the probability that I take this route? Which means, what is the probability that I have chosen R1 as my set of random objects throughout my algorithm, right? So that probability, time, the running time, plus the second route, that probability into the running time, so on and so forth. And that is the running time for this algorithm. So this is how we analyze most randomized algorithms. But let's see what happens now. We just try to follow that principle. Okay. So now the first thing to understand is what events to count. Okay. So in sorting, the object which dominates the running time is essentially the number of comparisons. Okay. So that is if we are able to count the number of comparisons we make, then the running time is proportional to the number of comparisons. For example, what do we do? Like splitting, like finding a pivot is like a very simple operation. And given a split, given a pivot, we are doing some number of operations by comparing all other elements with this and moving it to the left or moving it to the right. So that's all. So if we're able to give an upper bound on the number of comparisons, of course, expected number of comparisons, then that will govern the running time of our quicksort algorithm. So let's try to see how do we achieve this. Okay. So first we have to understand what is the probability space. So our probability space is when I say probability space, I mean given X, what are the possible random coin tosses do we make? Okay. But this is too big. Why it is too big? Look, we make first random coin tosses. Okay, we made some random coin tosses, and now you split. So let's look at the structure of this object which is underlying this algorithm. Then when you go left, you make some random coin toss. You make another random coin toss. So basically, what you are getting is basically tree of random choices that you make, and at the end, whatever you're getting is a sorted array, right? So basically, if we really have to think in our head, then we will have to think these kind of trees as a possible set, a possible objects in our sample space, and this is too big for us to like correctly define, not correctly, but let's say formally define that object, or and then try to work with. But there are clever ways of working with the same space, but not explicitly defining it what the space is. Okay, and we will see one good example just now. Okay, if you have any question, please ask any point of time. Okay, just like any normal class, just unpause yourself and like just ask question. Okay, so two things that we have to now do: what random variables to define and what are the events of the algorithm. Okay, so now so given an array A of size n, let QA be the number of comparisons of randomized quicksort on A. Okay, so this is the object which we want to count. Okay, QA. Now, what is an extra property of Q of A? Let's try to understand. Note that Q of A is a random variable, right? Because based on what random choices, what random tree we choose, okay, of choices, right? Number of comparisons could be very different. For example, here, if we somehow chose very object which is like not properly moving things left or right, then both sides you still have large enough problems to try. And so, for example, I could be very, very unlucky, and suppose I had n minus 1 and n. First, I choose n. What will happen? Well, left hand side is nothing, and my problem is n minus 1 dot 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 1. Okay, this can happen with probability of how much? 1 by n. Next, I get n minus 1. That will happen with probability 1 into n minus 1. And then I do this. But notice that here it was much easier for us because this is just a structure of tree, right? So what you do is basically what you have done. So if you want to think in a more abstract language, then we will have to say that our first pivot was nth ranked element. Second pivot was n minus 1 rank element, so on and so forth, right? But what is the probability of this? Let's try to understand what is the probability of getting these sequence of coins, right? N, then n minus 1 and so forth is like 1 over n factorial, right? And then at least for this selection of choices, the running time is n square, right? So as I told you, right, what selection we make at the end when we do expectation, the random choices we make and the running time corresponding to that random choices. So this is what we multiply. So if we would have taken this path, then our probability to get this particular path would have been 1 over n factorial times n square, right? So in general, notice that basically if you think about this algorithm, I did not try to say what random variables to define, right? So too big. But if you notice, this is actually is nothing but so don't think of array as like array as a position. Then basically at end of the day, when you're doing this pivot operation, you're basically giving permutation of 1 to n. This is what you will essentially be guessing, like but that's like not right way to say, because actually it's a tree, and you have to like if you really want to say in this terms of 1 to like permutation, then you have to say like some sort of in order, off order traversal, but we don't want to go into this. But suppose every possible choice was like 1 over n factorial, then it is 1 over n factorial, right? And we have n factorial, but then if we just did what we did, then we will get n square as our running time, right? But we know from previously that this is not the case, okay? So we need to be a bit more smarter, and how do we things? And why are we saving this? We will think for a minute. The reason why we are saving it, because if we have an array and we chose an element in the middle, then I will never compare an element between which are left of this element and which is right of this element. We never compare. So those kind of comparisons never come, and somehow we need to account for those comparisons also in our algorithm. Okay, so this is just to give you some outline of what we are trying to capture, and what we wish to achieve. Okay, so let's go back to, so all we have told you that Q, number of comparisons, is a random variable. Based on what choices we make, we could be lucky and we spend very few number of comparison. We could be unlucky and we could be spending lots of comparison. But we know what is the like upper bound on QA is. Now, to understand this QA, I'm going to define AI left and AI right with the left and right arrays obtained if let xi be the indicator random variable, which is set to 1 if pivot is of rank I in A, else 0. Okay, you get my point? So like if I have a rank, so for just for our own understanding, let's believe that all the numbers are distinct. Okay, let's just make a simplifying assumption, but it wouldn't matter. Assumption: all numbers are distinct. Okay, then then when I say rank, I mean fifth rank means the number which is in the fifth position in the sorted order. Okay, and let's fix that we are sorting from small to big. Okay, so when I say ith rank, it's like a ith ranked element in the sorting order. Okay, so let xi be indicator random variable which is set to 1 if pivot is of rank I in A, else 0. Right, and once given this this object we select as a pivot, AI left and AI right are the contents of the array which is left of this and the content of the array which is right of it. So now let's try to write this random variable QA. So what is this? I said, look, this random variable QA looks like this. Whatever it is, so I'm at array of size n, then I'm going to make actually n-1 comparison. So let's say that they are going to make n comparison because every other element will be compared with this element and either will be moved to left of it or right of it. Okay, okay. So this is what n is. Now, based on, look, as I told you, right? Now think of your random variable should capture, as I told you, right? That suppose this is my array, right? In next step, my algorithm could be like 1 and n-1. Maybe if I pick the second ranked element, then 2 and n-2. If I pick the third rank element, 3 and n-3, so on and so forth, right? So it needs to capture all those things. Okay, so now what I'm saying that, look, number of comparison is n and xi, which tells, look, one of these possibilities are going to happen. Not all, but one of them will happen. So if ith rank element is going to happen, then the total number of QA is upper bounded by n plus one of these set is set to 1, and number of comparison the left side, number of comparison the right side, and that's it. Okay, so this is just like counting number of comparisons in a gender. So this is how we have defined our random variable. We have set up our random variable is like number of comparisons is n any way I'm going to take plus what is the choice of my index, and then the number of comparison in the left of that index and the number of comparison in the right of that index. Okay, good. But notice each element of A has a probability exactly of 1 by n of being chosen. So what is an expectation of xi? So probability that pivot has rank I. And look, xi is an indicator random variable which is set to 1 if pivot is of rank I in A, else 0. So probability that expectation of xi is same as probability pivot has rank I, which is equal to 1 over n. So now let's just substitute this xi equal to, now we would like to compute expectation of qi. But before that, let's try to understand one more property. So random variable xi is independent of random variable qi left as well as qi right. In other words, expectation of xi into qi left is equal to product of their expectation, and same with the right hand side. And why is this true? Think for a minute. Look, the random coin toss which I do in the first step is different from what you do recursively in left. Like they are not correlated with each other. You can also formally prove it because, as I told you, right? You're like, this is a vague argument, but there's also a formal way of proving it. But if you write this is good enough. That the coins which you use for qi left and qi right they are different from the different, or they're independent of each other compared to the coin which I used for the first one, right? And new random coins that are independent of the coin toss is used to decide the first pivot, and only the latter decide the value of x1. So whatever the first pivot you make, that is the only thing which decides the value of xy. So since we are using distinct coin tosses at each recursive level, these guys are independent of each other. Okay. So now let's try to analyze via recurrence. So let Tn be max A, cardinality of A equal to n, EQA, be the worst case expected running time of randomized quicksort on arrays of size n. Okay. So I look at all array of size n, and T of n will be the worst case running time for this. But for a particular A, what we just now showed, that Q of A is the following. I can write this random variable Q of A as a recurrence like this. Now, I want to find the expectation of this random variable. So I'm going to use the fact, linearity of expectation, and the fact that expectation of xi into qi left is like, since xi and qi ai left are independent of each other. And look, this is also clear that once you made this choice of xi, what you compare left and what you compare right, they're completely independent. And like once you select xi and this, they get like, what is the number of competitions, they just get fixed. So this is what I can write it down. Now, what do I know about E of xi? Right? So this is same as EQA less than equal to n plus summation I equal to n 1 over n T of I plus I minus 1 plus T of n minus 1. Why? Because what was the property of xi? It was the ith ranked element, right? So I minus 1 element is after him, and like n minus I minus 1 actually. So this is why I have written down less than equal to, right? So this is what it is. Okay. So expectation of QA is nothing but I have just substituted everything, right? So this is what we wanted to compute, but this is something which is smaller. And what is this? This is the upper bounded by EQA, like, because I don't know what that array is, AI left, right? So I have said, look, let's substitute that with the worst expected running time on any array of size I minus 1. So this is why it is Ti minus 1, okay? And this is T of n minus 1. Okay, do you get how from here to here I got this, right? So I'm just substituting this guy is a, look, here AI left is a particular array of size I minus 1. But what is T of I minus 1 is it's the worst expected running time over all array of size I minus 1. So I have just substituted this quantity by something which is larger. Similarly here. Now, okay, there was nothing when we wrote, right, worst case of rent, or this is what we derived from here. Now notice that this equation holds for any array A of size n. And therefore what we can say, max of A, this is exactly what that is equal to T of n, is less than equal to this reference, right? So this holds for any A. So in particular, this holds for array which takes the worst running time. Okay, so now you get this recurrence, and the base case is T of 1 equal to 0, and now you can actually solve this recurrence, okay, by standard methods. I'm not going to give you details of that, but you will get that this is equal to order n log n, okay? So this is exactly the way we have solved, the way we are used to solving merge sort, quicksort, and all those, right? Oh, I have got divided into 2 parts. Let me add the running time of those, okay? So, but here, the division is not 1. So if you notice picture-wise what happened, that here I had X, or here I had array. Based on the random choices I made, I got 2 subproblems here. This is 1 subproblem, 1 subproblem, and this is 1 subproblem. Now, what is this tells me? Okay, what is my running time? Well, what is the probability of getting here, and then the running time for this? What is the probability of getting here and the running time of this? What is the probability of getting here and the running time of this? And this is exactly like, if you like, or the expected running time, right? So, well, so think of this way, that whatever may would have been the probability of getting to this, I have subdivided. Look, I have made my first choice, and this is a sub problem which I get. Okay, so I reach this sub problem with this probability and whatever the running time. So this is exactly how we analyze recursive algorithms or divide and conquer algorithm in general. But when you are doing a divide and conquer and probabilistic algorithms, so after your first choices, you have several options. And for each option, you achieve that with certain probability. So you sum them up, okay? And like you average them up, basically average them up. And this is exactly what this recurrence means. And you can solve this using normal recurrence relations that it solves to order n log n, okay? Basically, you can do what is this called? Guess and verify by induction, okay? Any question? I think it's a good time to ask questions before I tell you the second method to achieve exactly the same. No questions? Or I don't. Okay. So if I'm not hearing you, maybe you can write in the chat then. Okay. 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 So now I will tell you. So I wanted to give you first flavor of what you have seen before. Okay. I did not want to be smarter. So the analysis which I gave you before, this is not smarter. This is starting from the basic principle. Okay. I made one choice. I got several based on that choice, I could get several sub problem. So I generally think about this as like some sort of branching tree, and I get each branching, like each node of this branching, first node level of the branching tree with this probability. So this into whatever this is, this into whatever this is. So I just sum them. This is exactly what it is. Okay. So so I'm saying you could get this running time with this probability, you could get this running time with this probability. So this one, like this probability takes care of weighted average in the sense of running time. So think of this like, suppose here it was equal choices, but as we go down, notice what happens. Look, maybe if the problem got really subdivided into two equal half, then after that, when those subdivision you go, you are not going to choose an object. You are not going to create, what is that called? You are not going to choose from like 1 to n minus 1. You're going to choose 1 to n by 2. And those things starts to matter, but really visualizing them is a difficult task. And that is why like you just unfold one step and leave everything to recurrence, or leave everything to induction and let it take care of it. Okay. Okay. So, but here is a smarter way of doing these things. And somehow this is canonical example which is given everywhere, and I think it's a very, at least it gives you some intuition why the analysis we did is nice or correct. Okay, so we are still okay. So QA is the number of comparisons done on input array A, and now for I less than equal to j, and which is strictly less than a, let Rij be the event that rank I element is compared with rank j element. Okay, look, I'm using the word rank I element with rank j element. So this rank, I will tell you in a minute. Okay, it's basically, as I told you, in the sorted order, the comparison, like rank I element and the rank jth element. Okay, this is what it means. In the sorted order, the ranking of the ith, like which is the ith element in the sorted order, which is the jth element in the sorted order. Recall that we have simplified our instance by assuming that there is every like array consists of only distinct numbers. Okay, and what is an Xij is an indicated random variable for Rij. That is, Xij is 1 if rank I is compared with rank j element, otherwise we set it to 0. Okay, so this basically tells us that for every possible comparison, I have set up a random variable Xij, and this is set to 1 if in our algorithm these two numbers are ever compared. So what will be Q of A in this language? Number of comparisons in this language is nothing but summation Xij, right? Because Yeah, this is, so again, this is our unbiased estimator for number of comparison, right? So expectation is exactly the number of comparison which will be done in this algorithm. So QA, or which is equal to summation xij, is an unbiased estimator of the object which we are trying to compute. Okay, the number on the object which we are trying to compute. Okay, so this is not so, and now they hit linearity of expectation, and we say what is an expectation of QA is nothing but this expectation of xij, which is nothing but probability of rij, right? So we have moved our question to just asking ourselves, what is the probability that the ranked I element is compared with ranked j element? Okay. Okay. So our main question is, what is probability rij? Let's try to understand that. Okay. So suppose I have an array 7, 5, 9, 1, 3, 4, 8, 6. Okay. Now, so what is the rank? 1 will come first, so its rank is 1. 3 will come second, so 2, and so on and so forth. So whatever you see in blue is basically their rank. Like, so I'm writing their rank in the sorted order. Okay. So as such, what is the probability of comparing 5 to 8? Is probability R47. What is the probability of comparing ranked 4 element with a ranked 7th element? Okay. So I hope, like, so if you want to see in your normal array, what is the probability of computing 5 and 8, then, well, it is nothing but, in our language, the way we have written, it is probability of happening of R, 4, 7. Okay, I should have written without comma, but you will forgive me for that. So what happens if pivot is too small? Say 3 here. What is rank? 2. Now, if can 5 and 8 be compared at all? Like, or decision to compare 5 and 8, what do? You have moved to a sub problem. Okay, like in this selection, you are never going to compare 5 and 8 because every element is going to be compared with 3 or 8. Okay, but what more I want to tell you, that if both the elements which are trying to believe or compute probability, whether they are compared or not, if the rank of both of those is much larger than the rank of 3, then they will be moved to the sub problems, right? For example, here, look, they move to the here 7, 5, 9, 4, 8, 6, right? 5. So you have moved the comparison question to the sub problem. Okay, same we can say if we pick a number of 2 high rank, say 9. Now they might, all these numbers 5 and 8 has been moved to the layer. So the decision whether they will be compared or not has been moved to the sub problem. Okay. Okay. So, but what about if pivot is 5, which is rank 4? Then will I be comparing this number again? Will be comparing this with 8? Because yes, if we pick up 5, then you have to compare every number with this. So in particular, 8 will be compared to this, and then they will move. But notice, similarly, if I had picked up 8, right, which is the rank 7 element, then definitely 5 will be compared to 8, and they will move to the left-hand side. So, but what happens if you chose pivot, which is 6, which has rank 5, right? 5 moved to the left of 6, 8 moved right of 6, but will 5 and 8 will ever be compared again? Right? Look, once, so there's something which is happening. What is happening that I'm asking, will these 2 ranked elements will be compared? Okay, well, at any point of time, if I picked up some element which is bigger ranker than this, then I have moved the question to the sub problem. Something is smaller than this, I have moved the question to some other sub. If I picked one of these guys, definitely they will be compared. But if I picked something in between, they will never be compared after this, right? And also notice that once they are compared, they never compared. and you pick something which is ranked between these two guys, then you never compare this, right? So this is where you are saving. So imagine that you have a number which has rank n by 4th, and you have a number which rank is like 3n by 4, and you picked up some number which is rank is n by 2. Then the number which is n by 4 and any number which has less than rank this and more than, those numbers will never be compared. So those kind of like rank comparisons, those probabilities will be 0. So this is where you say that if I'm able to break, if I'm able to pick some guy between the ranks of two elements, then the comparison between these two guys never happens. Okay, so let's formalize this. So what I'm trying to tell you, so this is what I'm trying to tell you, that the event Rij happens if and only if ith or jth ranked element is the first pivot out of ith and jth ranked elements. Okay. So one direction is obvious, right? If you are going to pick I or jth ranked element is the first pivot out of this, then definitely you will compare them. But now I and j has happened. So as I told you before, if I and j happens, then definitely in that step, you have not picked up a pivot at that level. You have not picked up a pivot which is left of this. You have not picked up a pivot which is right of this. And you cannot pick a pivot which is between them, because if you pick the pivot in between them, then they will never be compared. So the only time they are compared is either pick one of these two as a pivot when both of them are in the same subproblem. So what is the point? So I'm looking at a particular subproblem, and in this particular subproblem, two guys are compared only if I pick one of these guys as my pivot. Because if I pick anything else, then either I move the subproblem to the next step, or they are never compared. Okay, so this is if and only if. Any question here? Okay, so we are still trying to understand what is probability Rij. Okay, and I claim that probability of Rij is 2 by j minus I plus 1. Why? Let's give a proof to this. Okay? This is a formal proof. So these are the elements in A in sorted order, right? So A1 to AI, AJ, AN be elements of A in sorted order. And let S be AI equal to AJ. What is the observation? We just saw if pivot is chosen outside S, then all of S either in left array or in the right array. AI and AJ are separated with a pivot when a pivot is chosen from S for the first time. Once separated, no comparison. So once AI and AJ, like, so if you AI and AJ get separated, okay, then you never compare them ever again. But AI, so this is what we proved last time. AI is compared with AJ if and only if either AI or AJ is chosen as a pivot from S at separation, right? So they remain together. At some point of time, they get separated. So, and once they get separated, they are never compared. And when does that happen? So only time that happens, just before separation, these two guys are compared if and only if you have chosen either AI or AJ as pivot. Okay. Now, what is the chance of the happening? That how many choices are there for this? Is like j minus I plus 1, right? J minus I plus 1, and there are two guys which are favorable in the set. Like what is Rij happens if and only if either I pick AI or AJ from this set. This is what we have said. So now we have broken down our big analysis to just, okay, what is the probability of picking two, like some good objects from the set S, right? Oh, the set S has j minus I plus 1, and the two elements are my good favorable cases. So it is just 2 by j minus I plus 1. Okay. So technically the analysis is, this is what it is. Now we will see what we are going to get from here. Okay. But any question? Okay. I hope I'm able to listen to all of you people. Okay. 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 So this is exactly this. because you are choosing the pivot uniformly at random from the array. Okay. Okay, good. So now you can ask, look, what happened here? So notice two guys are compared if and only if something happened. Now we have moved the whole computation to picking two elements from a particular set. So we have like, and look, we needed if and only if, because then only I can say event this is same as event this. So if you compute the probability of this, you have computed the probability of the event of your desire. Okay, and and this is why, like, now 2 by this is good, because we are choosing something uniformly at random. So uniformly at random, if I choose, what is the probability of choosing from here, right? Although if you notice, you're picking an element uniformly at random from the whole array, but whether two guys are compared or not is same as picking from some small subset there, right? So this is something which we have simplified, like, oh, I'm choosing an element uniformly at random, but whether two elements are compared or not, if and only if, not only you pick, you are definitely pick, but if and only if you pick from this small subarray, right? These two elements, and that is what we showed. Okay, so now, do you know what is this? How much is this? Do you know how to prove this? Do you know how much is this? Okay, I don't know.
Hello, sir.
Yes.
So in the previous slide, I had a question.
Please tell me.
So probability of Rij here is 2 upon j minus I plus 1. So
Yes.
I don't understand, why are you taking the total number of like cases to be this set S? I mean, why is it not the entire array? It's not clear to me.
Look, we proved. What are we interested in? When are you going to compare I and j? Okay. And what we managed to prove, I and j is compared if and only if, okay, you pick I and j from this set. Like, look, the point is, let's try to understand, right? Okay, so I'm trying to understand at the time of separation, because that's the only time when I could have compare I and j, right? So think of this way. So this is the time I have an array. So if I'm not comparing those two guys, it means they're together. Okay. After this, either I compare. So look at the time they are separated. They are separated, meaning one goes to the left side, other goes to the right side. Okay. Now ask ourselves, what happened at this step? Okay. Let's ask ourselves, what happened at this step? Well, if so, either I could have picked up elements from here, okay, or I could have picked up elements from here, or I could have picked up elements from here is I, here is j. Okay. Now, if I picked up any element from here, right? So look, you just now said that at this point of time they are getting separated. If they are getting separated, it means I cannot pick an element from here. I cannot pick an element from here, right? Although I'm doing uniformly at random, but this has happened. It means that implies that you have picked up an element from here, from this set. That's the only region you can get separated. So I and j get separated if and only if I have picked up an element from an element which are ranked between I and j. So it's an if and only if. So now so what is the probability of picking an element inside S? So I have broken down the question of comparing I and j to picking an element from a subset. So although I'm picking from everywhere, but those everywhere is not good enough for me for this event to happen.
Okay.
Okay. Okay. So only these guys are my good candidates for separation. Okay. And some of those guys are good candidates for separation. Like all these guys are good candidates for separation. But if I picked up not I and not J, they get separated, but they never get compared. So if I'm asking myself, what is the probability that they do get compared? So it means at the time of separation, either I or J has been chosen as pivot. Because if not, then Rij is 0. This probability is 0. It never compared. Like they are never ever compared. Okay. So this is why we are. So once you prove, so think of this way in probability. Suppose I wanted to compute probability of some A, some event A, and say, look, A happens if and only if B happens, right? Now, then the probability of A is equal to probability of B, right? So I have an event A which I want to get a probability. But maybe it is difficult to understand, difficult to analyze that event. Then I move to some other event which is easier to understand, easier to analyze, and I say, look, this probability and this probability are related to each other. For us, it happened to be equality, but sometimes we may not get equality. Okay? So, yeah. So we have just moved the event A to some other event happening, and for which we have very easy to compute. So this is what we did here, right? Aij is compared with Aj if and only if, right? Ai or Aj is chosen as a pivot from S at separation, right? So now you want to compute the probability of this event, right? And that is nothing but very simple, like 2 by this. Okay. Okay. Does that answer your question? Hopefully.
Yeah.
Okay. So, yeah. So, do you know how much is this? Okay. I'm sure most of you have seen it.
Log in.
Yes. But do you know how to prove this? Okay, good. But that's fine. So just to give you, because some idea, not much. So if you know, this is what ln n is. Okay. X equal to 1 to n. Okay. 1 by x dx. Okay. So what is this? This is like your integration is basically summing everything, like in some sense continuously. Okay. So I will tell you. I want to tell you that this is less than equal to summation 1 over k equal to 1 to n. Okay. And so let's try to draw this picture. This is cute. Okay. I will not do too much. So here it is. Okay. Here it is. Suppose I have 1, I have 2, 3, ... n minus. Okay. n plus 1. Okay. And now this is how 1 by x curve looks like. This is exactly what 1 by x dx looks like. Or this is why f of x equal to 1 by x curve looks like. Now at 1, so you draw. So suppose this is like, I draw here, I think this is like 1. So I draw, say, half, 1/3, 1/4. So if I draw this, if I draw 2.5, what will I get? I will get something like, I mean, I'm not drawing correctly. This is bogus drawing, but like, okay. So I don't know. I think my drawing is very bad. Okay. So it's like, it should be like, how to draw this? Okay, wait. Okay. I think I should be able to. Oh, this is not correct. This is not good. This is why I'm making mistake. Okay. So 1 and 2, 2 and 3, 1/3. Okay. 4, so on and so forth. Okay. Now you draw this, and how do I draw? It's like something of this nature. Okay. So if you notice, what is happening here is that, so this is my curve 1 by x. Now, what is this area? Is 2 minus 1, 1, right? So this is 1. Okay, what is this area? So look, this is, I'm always doing 3 minus 2 is 1. And if you notice, this is like half. So this is an area, this is an area, so on and so forth. Okay, and so this shows that ln n is at like greater than, less than equal to this summation. But what you can do very interestingly is that look at here, look at this point. Okay, this curve is what? This is again 1 into half. What is this area? Right? 1 into 1/3. What is like, so you will also get something like 1, like here, 1/4. So what I'm trying to tell you is that, look, if I just shifted this number by, so if I said, what about summation k equal to 2 to n 1 over k, then notice that this sum is below this curve, right? So this is less than equal to ln n, right? So if I add 1 in the left side, then I just need to add 1 in the right side. Okay, this is proved by picture. So this is like log n. Okay. Okay. So if you draw fx equal to 1, like I have just summed up integration and this. If you don't know, then just believe that hn equal to order log n. Okay. So now the question in, and how much is this? Summation j equal to n minus 1, 1 by j, and this. So this is, okay. We'll see this number in a minute. So let's not worry about this. So our analysis of quicksort. So expectation of QA is this, which is probability of Rij. And we just proved that probability of Rij is 2 by j minus I plus 1. Okay. So now I just substituted this number. Okay. Okay. Now, so this sum I goes from 1 to n minus 1 and j is greater than or equal to I. So I can write this as j going from I plus 1 to n, 2 by j minus I plus 1. Okay. And I took out 2 outside. Okay. And I also changed, if you notice, back to that j is greater than, strictly greater than I. Now, okay, let's see. Okay. Now I want to say that, look, here, what I'm saying that, look, j could only be larger. So I'm saying, look, this is upper bounded by delta equal to 2 to 2 by n minus I plus 1. Do you see why this is true? There's some magic happening here. Okay. So the best way to view this is like substitute I equal to 1. Okay. I equal to 1. So then what are you summing up to? I equal to 1. So 1 minus 1 is 0. Right. So you're summing up 1 by 2, 1 by 2, 1 by 3, 1 by 4, dot, 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 whatever it is. And now you just write down. So this is one summation. Other summation will be like how much? 1/3, 1/4, 1/5, dot, 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 and so on and so forth. Now, what I want to do, I want to count this way. You get my point? If I count this way, then what is happening? Is that true that we are counting this way? So this is what is written here, right? So this is what it is. For if I substitute I equal to 2, no, this was like 1 plus half, okay? And the next will be when I equal to 2, 2 minus 1, 2 minus 1 plus 1. No, this is correct, 2. So if I substitute I equal to, see, this is my mental torture, but it's okay. So I equal to 2, then j equal to 3. Okay, something, okay? So basically what is happening is that now what we're going to do is, or maybe not, this is much easier than what I was writing. Okay, let's just check. Okay. maybe you don't even have to do all this, or maybe we have to do. Okay, let's see what happened. So what is this summation is equal to? So first summation is like, why do we write this? Let's see. So what I'm saying, this is like 1 by 2 plus dot 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 1 by n minus, what is I here? I is 1. So n minus I is n, right? So I've just added n here, nothing more. I just added n here. Now, next summation goes from, if you notice, whatever it is. Oh, this is a bit weird. No, let us write it down. Okay, sorry. I think. Okay. Okay. So let's write it down. Okay, you can participate in the discussion of computation, which I'm very bad at, but it's fine. Okay, so it is 1 by 2 plus 1 by 3 plus 1 by 4, so on and so forth. Next term is like, what does it starts from? Okay. Next term it starts from, for I equal to 2, j equal to 3. Is it always half? Yes, it is always half actually. Half plus 1/3 plus 1/4 and so on and so forth. But it,
So first time it goes till 1 by n, and the second time till 1 by n
n minus
minus
1, right.
So
So this is what is happening, 1 by n minus 2, so on and so forth. Correct, sorry. And then it is nothing but what we have done here is that, okay, fine. So this is this term is upper bounded by this, right? Because it goes from 1 by 2 to I is equal to 1. So it is goes to n by 1 by n. This is fine. Next term, it goes from half to 1 by n minus 1, which is also fine. So this is fine. Okay. So this is fine. So this is the upper bounded by this. Is like, this is basically writing this in this term. Okay. So if you look at this sequence, you know it is going from 2 to, you are moving, you are only going to go to some, like one term is some decreasing, and this is what this is showing us. Okay, but this is not too much important anyway. And why did I write this? Because to show that this is nothing but it is h of n minus I plus 1 minus 2, which is upper bounded by hn, and we have seen the upper bound on hn is like so. But there are some n such terms, so 2n hn, so you get order n log n. Okay. Any question? So one question that before we get into break, so that we all like to ask, where do I get these random bits? Okay, are true random bits available in practice? And the question is not. Actually, you have to buy them. They're like resources, and there are a lot of things in, like, lot of things which you can do using randomization. There are a lot of questions like how to make these pseudo random generators and how to de-randomize these randomized algorithms, and they form a course in itself. Okay, but we will not get into those kind of questions. So is there any question on the quicksort? Because after the break, we will deal with something very different. Hello?
Yeah, no questions, Saket.
No question, great. So let's take a break, and then we'll come back and do something different.
I have a question, Saket.
Please.
How tight are these analyses? Like, can we actually prove lower bound of in login for a randomized quicksort?
Yes. Because whatever it is a comparison-based sort, right? Randomized or non-randomized, right? Right? And what do we know about comparison-based sort? That no comparison-based sort can take less than n log n. This is just because look, at the end of the day, whatever may be, randomized or non-randomized algorithm, it has to distinguish between all sequences. You get my point? So So there are, like, this is how the lower bounds are made. Even for deterministic, if you have seen that it is log of n factorial, we can buy the same kind of argument even in the randomized setting, and you can show there's some omega n log n if the only thing which we are going to do is just comparison. Okay, but this is one kind of lower bound, and the other kind of lower or upper bound, however you want to say, we will show is that this we will achieve the expectation with very high probability. Okay, so yeah, so if expected running time, we are going to achieve this with a very high running time. It means there will be some instances for which this kind of running time will be achieved, but then this is a lower bound for this particular algorithm. You get my point?
Yeah.
Right. So once we get the quicksort result with in terms of high probability, right, and basically when you say high probability, what does it mean? You are able to say, look, it is within this particular range. It doesn't go this much or it doesn't go this much. And if you're able to prove this, then also it will imply that there are some set of instances where we shouldn't be able to take much less than that. Okay, but yeah, but there is a lower bound even just from the information theory that no algorithm will take. In particular, even randomized algorithm cannot take better than omega n log n if comparison is the only thing which we do or compare in the algorithm.
Okay. So
Okay.
it's based on information theoretic lower bounds.
Yes.
Okay. Yeah. Thank you.
Okay. So we'll see some probabilistic inequalities and examples, and I understand that some of you might already have been bored by just looking at some routine things. So just to make slightly interesting, okay, let's do something like this is completely on prompt, but anyway, I plan to teach this, so this is not that bad. So suppose I only have given you coin, like say an unbiased coin. Okay, and I said you generate a number uniformly at random among or which is same as like, how will we do it? How will you go about it?
You pick each bit of the
Okay.
of
So
your number.
Yeah. So what William is saying is that, well, the way I have written down, so I know that let's fix some k bit number. Okay, k bit number. Notice that at every place I'm going to get head, then I'm going to put 1. If I'm going to get tail, I'm going to put 0. Then you notice that by this I will be able to generate all k bits number. K bit number. So our algorithm will just do following. Okay. So our algorithm can just do as follows. We just like for the first bit, do coin toss. Second bit, do coin toss. So on and so forth, right? So this is the way, and since we have been given an unbiased source of like one unbiased coin, we are able to use this to get as large number uniformly at random, right? Okay, but what about, okay, this was all good. But what about
Yes.
3? If I wanted to generate a number, one number between 1 to 3, okay? I'm not going to give you an answer for now. This is your puzzle of the day. Okay. But what I wanted to do is something more simpler. Okay. Let us. Okay. So you suppose. So this is a very. So why did I say this? Look, all we know is a coin toss, right? And then how do I generate this? Using this, can I generate all small numbers uniformly at random, like using just this coin toss? So think about it. So what you just saw is that, well, if the numbers are between 1 to 2 power k, I can do k coin tosses, and from there I can get an information about a number from 1 to 2 power k uniformly at random. So you notice that if you're interested in generating numbers from 1 to 2 power n, all you need is n bits, right? So n bits are good enough. So if you want to generate a number uniformly at random from 1 to n, log n bits are good enough for your purposes. Okay, and these things are used very crucially in many applications. But this is not what my question is. My question is, suppose for now I can only give you the following oracle. Okay, so you are given an oracle. Okay, this is an oracle which I give you. What I mean by this oracle takes two things. Takes actually one thing. Takes a number n and outputs a number from 1 to n with probability 1 over n, or this is what I mean by uniformly at random. Meaning for every j from 1 to n, probability that oracle outputs j is 1 over n. So this oracle is given to you for now. Okay. Okay. Here's my task. Okay. So here's a task. After all, we are doing big data, so we should be able to do. So online uniformly at random. Okay. So what is this? So numbers are coming x1, x2, dot dot dot, xq. Okay. These are the q numbers that are going to come. At any point of time, you see xq and you see some xi, and then xi goes away. Okay. 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 So I don't have. So let me add a page. Okay. So what output do I want? Okay. Output I want. So think of this way, like x1, x2, they're coming as some flow, like in a what do you call some what do you call in an online fashion. In an online fashion, or in a stream, whatever you want to call it. Okay, and I want to output a number, some x, such that x is in x1, x2, dot 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 xq, and probability of x is 1 over q. So this is like I want to output a number from 1 to q uniformly at random. Okay, but when ith number comes, you don't know how many numbers are yet to come. You get my point? Otherwise, if you knew the total number, then what would you tell? Okay, well, I mean, You could just run your oracle and do something, but you do not know, right? You have no idea about the number of items which are supposed to come, right? So this is our first question in the big data. I want to output a number uniformly at random from the stream. Is the question clear?
What's your memory, Saket?
Oh, one location.
Okay.
You can store a constant number of xi's.
Okay.
This you can do. Constant number of xi's.
So okay.
Okay. So question is very clear, right? I have numbers coming, right?
Do you
Yes,
have
Fred?
any assumptions? Do you have any assumptions on the structure of the stream?
No, nothing, Fred, nothing. They are adversarial.
No distribution, anything? Okay.
Nothing. So, for example, if I would have
But-
asked you the following question, okay, let's go slightly simpler. Okay, how many items are there in the stream? This is easy, right? Right? You keep a counter, increment it.
But the numbers are integers.
Fairer, yes, they are integers.
Okay. Okay.
So log n bits is good enough, right? I can keep a counter. If I just wanted to count the number of elements in the stream. Okay, but here I want to output a number from the stream, and I want to show to you that whatever I have output, it's with probability 1 over the size of the stream. Okay, and at any point of time, you can only keep few of these xi's, constant number of xi. Okay, so like this is a very basic primitive which we will be using in all our big data algorithm, right? So this is why I'm trying to do this like in a what do you call it? In a slightly nicer fashion. So you see, at any point of time, you have to make some decision. When xi comes, you have to make some decisions, like which one to store, which one not to store, what to do. Because at the end of this process, look, xi is gone. So even if so one way would have been to do the following. Okay, I just do the counter q, and then on the q I run my oracle. It gives me some index, and I say take that number xi. But well, have I kept that in my memory? No. Did you get this idea of the solution which I proposed? I'm saying one potential solution and one potential flaw is the following. Keep a counter, say of log q bits. That's nothing. You just keep a counter, and when a number comes, increment the counter. Okay. So at the end, we have suppose this counter is C. What does we have C storing number of items. So oracle on this counter returns a number between 1 to q, and I could have said, okay, and algorithm could say return, suppose this is z, return xz. Unfortunately, I have no memory for this. Unfortunately, xi's are gone. So you understand the kind of difficulties when we deal with big data. Even the basic set of questions, like because of the memory requirement or because of a small space, like even a small set of things which we take granted on static data, like becomes a difficult question. Like, I just want you to like I'm happy with anybody, those who have not seen it, to propose a solution.
So what about storing two values?
Okay.
One is the counter
Okay.
and another is the element. And I'll change, I'll store the current element with the already stored element with probability 1 by I.
Okay. Yeah. Then we
Ith element,
yeah. Then we don't.
but
you're
it's
right.
a hunch, but it may not be correct.
Yeah. So it's correct. Okay. Okay. So let's prove this. So let's see what solution has been proposed, and let's see why this is correct or wrong at base. Okay. So what is an idea? So the idea is very simple. Okay. So as Aditya pointed out, so we have these numbers x1, x2, xi coming in. So in the beginning, x stores x1, or let's say not x, okay, x dot xa. So suppose some variable y which stores x1, and we have a counter which stores number of elements seen until now. And now what is it proposing? When xi comes, do as follows. Okay. So what he wants to say, okay. So basically at this point of time, what is C storing? I. So replace content in Y with xi with probability 1 over I. Okay. Okay. So with some probability, I decide to replace the content in Y with xi. And what is the probability? 1 over I. Okay. And I claim that this is good enough for our purpose. Okay. So let's see. Okay. So suppose Y stores some number xj. At the end, you return it. So I have to show that, or in fact, it is true about anything. So let's see what happens here. x1, x2, dot, 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 xj. So when does this happen? Okay. So at this, so when will Y store xj? It will store xj, Y stores xj if in the jth step we replace Y, we replace the content of Y with xj, content of Y with xj, and from j plus 1 onwards, xj plus 1 dot 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 xn are not put in Y. Okay. So this is what happens. So what is the probability of getting, what is the probability of this? So this happens with probability 1 over j. Okay. And what do we know? From xj plus 1 to xn does not get. So that implies it's a product j plus 1 to n 1 minus 1 by j plus 1. Like with probability 1 by j plus 1, we put him in the content, and with probability 1 minus 1 by j plus 1, we do not put him in the content. Okay. So this is why this is the probability of xj in the our memory of Y. So now what is this probability? This is easy to compute, I hope. 1 by j. What is this? J by j plus 1, right? Into next will be, if I put j plus 2 is j plus 1 by j plus 2, so on and so forth. What is my last term is going to be
1 by n.
blah, blah, blah. Wait.
Minus 1 by n.
Yeah, so last one is n, right? So it is n, so it is n minus 1 by n, right? Now you take your red knife, cut, and what do you get? 1 over n. So this is our first algorithms which we have made on big data, that how to uniformly at random return an element in the string. Okay, any question? Okay, so let's make our life, let's ask more question. So this was okay because we wanted to return one element. But what about if I wish to return so suppose we had this x1, x2, xq, sorry, x something, xi, and . Now what I would wish to do, return say k size subset, return a k size subset of x1, x2 dot xn, xq uniformly at random, right? So what we did up until now, we returned a one size subset of x1 to xq uniformly at random. But I said, look, now I need actually k size subset. What do you think we should be doing? Suggestions, ideas? Okay. So basically now what we'll do, so it's not very hard, but we exactly did do what we did previously. So now, but now we will not keep one memory location. We'll keep k memory location, 1, 2, k. Okay. So, and you run this. So while stream is not done, what will we do? So for the first k elements, we just place them into first one, second one, and kth one. Okay. Okay. So initially m is set to 0. This is our counter. Now you set m to m plus 1. Okay. And xm is the current item. Okay. Now I check if m is less than equal to k, as I told you, what will you do? Well, then Sm, or let's call this array S, 1 to k. At Sm, I'm going to assign Xm. Okay. Else, so interesting thing is that what happens if you go beyond this? Okay. Now what we do, R, you pick uniformly at random, okay, in range 1 to m. Okay. If R is less than equal to k, then what will you do? You replace the content with xm, and that's it. End while. Output s. Okay? So basically what is, and alternatively we can say that what is happening here is the following. Okay, like when xt arrives, t is greater than k. Okay, we decide to choose it for inclusion in S with probability k over t. Okay, inclusion in S with probability k over 2. Okay, but this is not all, right? Yeah, it will be in S, but which index? Okay, right? With probability k over t, and if it is chosen, okay, and if it is chosen, then we choose a uniform element, okay, from S to be replaced by xt. So the process is as follows. So here is our S, okay, okay, and the tth element is here. We say what is the probability that we should be picking him in the S? That's like k by t. Okay, but which element should be replaced, right? Okay, so then there's another. Okay, so one of it, which is same as what we did here. Like we just picked up a number in the range 1 by like between 1 to m, and if the number fall into 1 to k, we replaced it with that number, like we replaced with that coordinate with this. And what do you think is the probability of this? Probability of returning is basically this is my another of those. So suppose, okay, then x, or what we use the word S content is an element of q choose k, means all k sized subset of x1, x2, xq. Okay, so S m, so Sm in this probability that you fix. Oh, this is not the right way. Okay, say let x be this some subset. So probability that Sm equal to x is equal to 1 over q choose k. Okay, so basically, so this is your, okay, I gave you an algorithm. I would like you to do probability computation yourself, just like, otherwise we'll discuss it next time. Okay, so here is an exercise. Look, these are simple exercises, but it will help you get through some of these ideas. Prove that the algorithm outputs a random sample without replacement. We do not replace, without replacement of size k from string. Okay. Okay. Any question? Is the algorithm clear? So what algorithm does nothing, right? So it's just maintaining some like some auxiliary space of array of k size. When a new number comes, it uniformly at random decides whether to pick him or not by choosing a number. So if some index came, okay, fine. like you just from this, if that number has come like, okay, fifth, oh, if it is less than k, I go toss him out and put him there. Okay, okay, okay. So which is same as what is the probability that he will be chosen in the possible outcome? Well, that is like k choose 2, but which one should I replace him with? Okay, so that's like choose which of the location you want to replace with. That's 1 over k. That's like 1 over t. Okay, but try with 2. It's really fun. It's not very difficult or something, but it is, in my opinion, it's quite illustrative. Okay, but if we are not able to do, then we'll talk about at least this algorithm next time. Okay, any question? Okay, so now I'll go back to what I was trying to do. Just I thought that you might feel a bit bored, so I told you your first algorithm for what is that called? Algorithms for big data. Okay, but now we will do. We'll go back to asking some very basic question which we will need to ask quite a lot in our course. Is like, and to do that, we need to use some inequalities like Markov's inequality, Chebyshev inequality, Bernstein-Chernoff Hofding bounds, and some balls and beans kind of examples. So this is what we will do. Okay, so let's see. Okay, so now we are in the situation where we are considering a flipping of fair coins n times independently, and head gives 1, tail gives 0. And this is a very natural question we ask, how many ones? And you can say that, look, there's something called binomial distribution. So we say, look, we have k ones with probability how much? So imagine that I have done n coin tosses, okay? And I want k exactly heads. So I choose which all k places will I get head. So n choose k, okay? And at those places, what I want 1, and every other places, I want 0. So 1 by 2 power k, 1 by 2 power n minus k. So we get n choose k, 1 over 2 power n. Okay, so if you look at this space, okay, so what you see below is the number of what is the probability of getting 0 head? So probability of getting a 0 head is this. And now we are only doing 2 coin tosses. So if we are going to do 2 coin tosses, what is our sequence look like? Either head head, head tail, tail head, tail tail. So notice that we are going to count, okay, what is the probability of getting a 0 head? Right? 0 head means we should get tail and tail. What is the probability of that? 1/4. So this is what this represents. So here it tells what is the probability of getting that particular number of heads. So 0 is this. What is the probability of getting 1 head? So either you get head head, or either you get head tail or tail head, right? That is half, because this you get with probability 1/4, this you get with probability 1/4. So this is exactly what this peak means. Okay, and what is the probability of getting 2 heads? It's just head head, which is 1/4. Okay, let's see another picture. Now we are doing 4 coin tosses. Okay. Okay. So one question to ask maybe at this point of time, what is an expected number of heads if we do n coin tosses? Okay. So let's ask ourselves at pace. So we are doing n coin tosses So coin toss 1, coin toss 2, coin toss n. And I'm interested in what is the expected number of coin tosses. Sorry, what is the expected number of head? Can we set up some random variable for this? So suppose x is my random variable and it takes from this, and what is this real number? So it's basically given a sequence of head, tail, n. Okay, I shouldn't be writing this. This is a terrible notation. So given a w in head, tail to the power n, this is equal to number of heads in w. So what are possible values x can take? Okay. Possible values x can take are 0, 1, 2, n. So now I can definitely define what is an expectation of x. What is an expectation of x? From first principle, if not from the second principle. Anybody? But come on, guys, this is not very hard.
I would say n over 2 second.
Yeah, but that's an answer.
True.
Yeah. Yes, this is right. But like, yeah, they're like, if I had to do from the first principle, what will I do? Right? What is an expectation of x? Summation, the value it takes, x in R. So this takes x into probability that x equal to x. Right?
Yes, yes, yes.
I don't think there's much to this. Okay?
No, that's it.
That's it. So what is this? So now if I could just do like a brute force summation, the other thing is just put j in natural number or j equal to 0 to n, j equal to 0 to n, j into, right, n choose j 1 over 2 power n, at least the setting which we are in, right? And if you, in fact, and at the end you will get n by 2. So, but even if you had a coin toss with probability p and 1 minus p, you would have got, if our coin tosses were like head with probability p and tail with probability 1 minus p, you would have got here n into p. But if you do this, like run this estimation, you will get this. But there's a sleek way of doing it. What will be a sleek way? What do you think is a sleek way? So let's say x1, x2, xn are random variable. Okay, and what this means? Okay, xi is 1 if ith coin toss is head, 0 otherwise. So now what is your x? Is summation xi. So what is your expectation of x? Is summation expectation of xi, which is, what is probability of xi? It's going to get head with probability half, right? So this is going to be summation half, which is n over 2. That's it. Okay. But why did I bring this up? Okay. Good. Let's look at my picture. So what is this 4 denoting here? This is my expectation. Okay. And so if I had 4 coin, like if I had 8 coin tosses, then we believe that, okay, 4 is an expected number of coin tosses. And what is the probability of 4 is something here. If I am running 8 coin tosses, let's look further. If I'm doing 16 coin tosses, what is my expectation? 8. It is here. 32, So as n increases, if you notice, right? So most of the like it seems to say, this picture seems to say, look here, like there could be some numbers here, like very low probability, but they're close to, like most of the mass, by mass means what I mean. So look at 1, which is probability, right? So the like probability of, say here it was like 120, 256 is 128, right? So number of heads is within the range, say 100 to 150, like, or within the range 128, like slightly here and there between 128, is almost close to 1, right? So, and as n grows, this, like the mass, the probability mass of number of heads just gets closer and closer to the expectation. You do more, you do more, you do more. Okay? So, like more and more coin tosses we do, we talk about more and more randomness, but it is not that randomness. Okay? So this is what is known as concentration of mass, and this is a very special case of what is called law of large numbers. So when I say concentration of mass, it means, look, for the quicksort, what we did, we computed expected running time. Now I can ask, okay, fine. So this running time is achieved with what probability? So is it really the running time closer to the expectation, or it deviates from expectation quite high? Okay, and what this picture is telling us that, look, in many circumstances, mass concentrate around the probability or the mean or the expectation. And what is the law of large number tells us? I don't know how much if you know Gaussian distribution, but I'm not going to talk about Gaussian distribution, but this is what is called Bayes curve. So what it says that for n large enough, the middle portion of the binomial distribution look like a normal or Gaussian distribution. So basically they look like a bell curve, which basically means that the probability that you are far apart from the mean, like the number of heads here and the number of heads here is too low. So like number of heads with number of heads which are within this range and the number of heads which are within this range is less than, like, or it's like closer to 0, right? So it's like maybe 1 over some poly n, or maybe 1 over some exponential in n. So the probability that number of heads is here or the number of heads is here is less than equal to 1 over exponential. So most mass is, or so basically what it means to say that, look, number of heads is like, if I had like n by 2, so n by 2 minus something, n by 2 plus something, most number of heads, what is the probability of this is concentrated around there. Okay, is the idea clear, right? So why am I bringing these things up? Because I want to, like, okay, so this is a bit of a listing. Okay, so let me give you a very concrete example. Okay, so what I wanted to show, so random variable q is the number of comparison made by randomized quicksort on an array of n elements. So suppose I want to say what is the probability that q is more than 10 times n log n. I want to suppose this is true, right? That q is more than, probability that q is at least 10 n log n is less than or equal to c. And we also know that q is at most n square. So what is an expectation of q? So look, expectation of q is like what? Summation of probability of something into running time, right? So suppose I can break this into summation like at most 10 n log n, right? So running time is at most 10 n log n plus summation running time is at least 10 n log n here. Now all these terms, what can I say? Well, probability that Q is at least 10 n log n is upper bounded by C. So I can say that, look, so probability that something is less than 10 n log n is at most is at least 1 minus C, right? From this inequality, we can say, look, probability that Q is at most 10 n log n is at most 1 minus C, right? So I can write it into 1 minus C. I can take it out, and how do I say? Okay, oh fine. And so this is like 10 n log n times of Q okay. So how many terms are here, right? So this is like summation 1 to 10 n log n, right? But we also have to multiply with probability this 1 over 1 minus C. And 1 minus C into, say, a square. And what will be for other thing? You just took the worst running time and you multiplied with C. That's it. Okay. Or, okay, this is not clear. Then let's see how the other way to say this will be. Okay. So now either I have my running time is 10 n log n, or my running time at most 10 n log n, or my running time is more than 10 n log n, right? So what does so this is why I wrote here, right? Probability is this. So this all automatically tells us that, look, running time is this. So when I say at most 10 n log n, everything is counted here up until 10 n log n, and this is why this person writes it here, because this is actually, it is 1 minus C into 10 n log n plus other is C times the worst running time, n square minus 10 n log n, at least this much. Now this is at most 1, so 10 n log n plus whatever this is. Okay. Now what are we achieving from this? So how do I say, so for example, if I could show that C is like, well, C is like 1 over n square, then this term, right hand side of term, is vanishes, right? So I'm going to achieve this running time like 10 n log n with very high probability. Okay, so we will see many examples of this throughout the course, but the basic question is, how do you bound this? How do you say probability that Q is 10 times more than its expectation is what? Okay, so this is a basic question which we'll try to address next time, like what kind of inequalities we can do or come who helps us bound the tail inequalities. How far away from the mean, how far away from the expectation you are. So in terms of our binomial example, right? So what we want to say that, look, what is the probability of being far away from the expectation? Can we bound the probability of being here or being here? So this is already true with respect to what you call binomial distribution, because application of law of large numbers. But the corresponding set of examples, so the problem, or we will consider, we have to prove ourselves that, look, this algorithm is far away from its expected running time with small probability. So for example, if it is expectation is this, then we will like to upper bound the probability that the running time of our algorithm lies here or lies here, and that we would like to upper bound with small probability. So what will the alternate point of saying that, well, actually for this input, you are going to be closer to your mean more often than not. Okay, and so this is something for which we need what is called tail inequality. Okay, that we would like to bound the tail of possibilities with small probability, and to do that we need some methods, some inequalities, and this is something which we will see from next time onwards. Any question? But I think this is a good time to stop here.